Hiya both. Hope you're both well and looking forward to a break from schoolwork next week, which you should definitely have. Um, so this is our Wednesday lesson. I guess you'd have a lesson with Mrs. Ferrand as well today. I haven't checked. So I'm going to do two different things in this lesson. This video's to do with the Mrs. Ferrand stuff, the differential equation stuff that you've been doing. So far, with Mrs. Ferrand, I know you've looked at integration techniques and some differentiation techniques as well. And all of that really is preparatory work for the main thing that we have to do in Unit 4, which is differential equations. Now, I am taking the approach of starting from scratch. You might already know quite a bit about differential equations from physics, but I'm going to assume nothing and just take it from scratch and build it up from there, which is why I asked you to read pages 55 to 59, because they serve as a introduction to differential equations and show you how to solve some simple ones. The whole idea of solving a differential equation needs to be carefully thought about as well, because it's not the same as solving an equation, an algebra equation, like you might have done for years in normal school. Okay, differential equations then. What are they, first of all? Well, if you read this page, you will see that a differential equation is an equation that contains a derivative. That is a dy dx term, or possibly a d2y dx squared term. And then also contains the basic variables as well. Obviously, differential equations can be incredibly complex and have many variables involved in them, but we're sticking to just having two variables, x and y, and obviously you can use whatever letters you like, but for learning it makes sense just to use x and y, and dealing with quite simple differential equations really. So these are all differential equations here, and as you can see, they contain dy dx's. These two contain d2y dx squared terms and other terms as well. Okay, so the first thing you need to well, there are basically two concepts that you need to be aware of. You need to be aware of the order of your differential equation, and you need to be aware as to whether or not it is a linear differential equation or not. In this course, we are only going to deal with first order linear differential equations and second order linear differential equations. Okay, so the page then goes on to explain what we mean by first, second order and linear. So first order are ones that just contain a dy dx term and also the variables themselves, x and y. So these four here are all first order differential equations. Second order differential equations are ones that contain a d2y dx squared term. They might contain a dy dx term as well, and they might contain the original variables as well. But if they have a d2y dx squared term, then they are second order differential equations. The second thing to understand is whether something is linear, an equation is linear or not. So basically, to be linear, the variable on the top of the dy dx term, in other words, the y, for all the ones that we're doing, has to only have terms that are separate from one another. Explain that very well. They can't be like multiplied together. So you can't have a y times a dy dx or a dy dx all squared. They would be non-linear. The x can be as complicated as you like. That doesn't have to be linear. The x can be any functions you want it to be. So these two equations here, they are actually both linear equations because although they contain some complex stuff like the sine x there, the actual dy dx terms are separate from one another. So you've got d2y dx and y there, they're separate from one another. There is actually a non-linear first order differential equation amongst this bunch of six, and it's this one here. So it's first order because it's only got dy dx, but it's non-linear because we've got a y times a dy dx there. Okay, so there's then a little exercise which is really not that difficult to do. So what's the order of these differential equations first of all? Well, that's obviously first order, second order, first order, second order. And then which of them are linear? Well, let's have a look through. That's linear, that's linear, that's linear, that's not linear. Okay, and the reason that that one is not linear is because we've got dy dx which has been times by itself, and that makes it not linear. So we will not be able to solve that one in this course. However, we will be looking at techniques for how we would go about solving the other three as the course goes on. There we go. So, solving a differential equation. What does that even mean? Well, here's the thing. It does not mean the same as solving an algebraic equation. That's what this first bit says here. Solving a differential equation, say this one here, is to find a function of y which when you sub it into here works and gives you the right answer. So when I say the right answer, I mean the left and the right hand side match. So you're trying to find a function of y which when you sub it in will give you something that makes sense. Now what we're going to discover is that there is not one unique answer to that. I'll show you why now. So you get like a family of solutions that would work called the general solution. Okay. Now these two here, simple linear differential equations, are the sort of ones that you will need to be able to solve actually in normal maths. We'll get onto the ones we're doing a little bit later. But let's just go over how you actually do these now. I'm actually going to do these. It explains it all here, but I'm going to do it myself so you can watch me doing some maths. I've got some paper here. I'm just going to write the first one out, which is dy dx is equal to 2x plus 1. So there is a typical differential equation. And I'm trying to find not the value of x or the value of y. I'm trying to find the function y equals f of x, which when I sub it into the left side and the right side, the two sides match. So in this particular case, because I've got the dy dx separate on its own on the left and a function of x on the right, I do that, and you'll notice already, by integrating both sides. And integrate the left hand side, it becomes y, and I'll just write out, I won't actually do the integral, I'll just write it out first like that. And the right hand side, I'm about to integrate the 2x plus 1 term. So if I do that, I end up with y equals 2x integrated is going to become x squared. I forgot to integrate for a minute then. And then the 1 becomes x, and we have a constant on the end c. And that is the answer. That is the actual answer to the question I asked, which was to solve this differential equation here. So it's not an answer as in what's the value of y, what's the value of x. It's a function itself. So by solving it, we eliminate the derivative term. And we just get a value of y, a function that allows me to find a value of y for a given value of x that I sub in. Now the interesting thing about this solution is that it is not unique. There are many versions of this, families of this, that all solve this. And that's because it has this constant unknown thing on the end here. If I wanted to know what that was, I'd have to have more information in the question. But for now, just to prove that this works, let me just choose a value for c, say 10. There we go, y equals x, a very simple example of this. Y equals x squared plus x plus 10 is an example of that general solution. I should write that, that's called a general solution. If you must know, this is called a particular solution. It's logical. Okay, the language is logical. This is called a particular solution. And this should work in here. This should make the left and the right hand side be equal to one another. And clearly it does. Because if I'm going to sub that in there, I'm first of all going to have to differentiate it. Like so. And now I can sub that in there, which will give me 2x plus 1. And the right hand side also says 2x plus 1. Hallelujah, it's correct, it works. So that function solves that differential equation. And it's not exactly rocket science to see why. Okay, so that, believe it or not, is solving a differential equation. Pretty much the simplest one that you would ever get. Now let's step the difficulty up a little bit by looking at the second one. dy dx is equal to 2xy. Okay, now, at first glance it doesn't look that much different from the first one, but there is a crucial difference. And it's this fella here, this y here, is messing us about. Because we cannot integrate both sides to turn it into y equals the integral of this, because we don't know how to integrate this y term. We only ever integrate functions of x separate from other variables. So, to solve this, you have to do something a bit weird. What you have to do is separate the variables. You have to separate the variables. And what that means is anything that's got a y in it goes on the left, and anything that's got an x in it goes on the right. So if I divide by y, I'll get dy over y, and then times by dx. At the same time, I'll get that. So the weird thing that's happened there is I've actually split this up. So we're no longer thinking of this as a single entity. We're thinking of it as a fraction with with a top and a bottom that can be split up. And we're not going to go too much into worry about why that's allowed, because it does seem a bit weird. Just accept for now that you can do that. Okay, and we get to here. Now, the next step is the clever one, because what we now do is we think of this as two expressions that I want to integrate. So I just stick integral signs on both sides. If that is equal to that, then the integral of that must be equal to the integral of that, like so. And I have an integral here to do in terms of y and an integral here to do in terms of x. And by doing these integrals, I will get rid of the dy and the dx bits here. And I'll just have y's and x's and a constant in my result. So the integral of 1 over y is, I don't know if you remember this one, we've done it quite recently, it's the ln of y. Yeah, now technically you're supposed to put the y in modulus signs like that. Okay, so it's ln of mod y, like that. And I don't need to put a plus c there, because I only need one constant in the whole thing. So I'll just integrate this side, and then I can just put plus c there, like that. Okay. So next, I'm trying to make it, I mean, I could leave it like that. That is a solution. Okay, but very often they want the solution in terms of y. So I'm going to have to make y the subject by doing something to both sides. And the first thing I'm going to do to both sides is I'm going to e both sides. So if I e both sides, I'm going to get minus plus or minus y. Okay, because when I e this, I get e to the mod y, but well, let's just write. I'm going to get mod y. I'll do an extra line to what they do. Mod y is equal to e to the x squared plus c, like that. Okay, and now what I'm going to do now is slightly alter the way this looks. If I've got something raised to a power of two things added together, there's nothing to stop me writing it like that. Got some more paper. Yeah, there we go. And then I can transfer the e to the c to just be a constant a. And because that constant could be plus or minus, I can lose the mod sign here, because the a can incorporate whether or not it was plus or minus. It's hopefully you understand what I'm saying there. the mod sign becomes kind of irrelevant at this point, because the constant I've chosen, big A, could be plus or minus, and that can take into account, depending on other things that you find out in the question, whether or not it's plus or minus. And this, put them in a box, is the general solution to this. Okay, so again, that's a general solution. So the next question is, does it work? So let's, again, choose 10 for the value of A there. And this would be a particular solution. And if I sub that into there, it should match up on the left and the right side. So let's see if it does. So here's the original differential equation. dy dx is equal to 2xy. So let's try subbing in to both sides of this. Well, if I'm going to sub it into the left side, the first thing I'm going to have to do is I'm going to have to differentiate it. So dy dx is equal to, right, this is chain rule, which I believe you've done recently with Miss. I've got a function of a function, e to the x squared. Okay, I refer to the x squared as the inner function and the e as the outer function. And to differentiate this, okay, you need to differentiate the outer function, which is the e, as if it was e to the x. Get the answer, which for e is e to the x again. But don't write e to the x, write e to the whatever the inner function was. So the 10 can just be written in front. So it's going to be 10 times e to the x squared, like that. And then you multiply that by the differential of the inner function, which is the x squared. So I multiply that by 2x, like that. This gives me 20 x e to the x squared. So these fellas here, I've just underlined, I'm now going to sub in here, and this one here, I'm going to sub in here. So if I sub that into the left-hand side, I get 20x e to the x squared. And the right-hand side is 2 times x times 10e to the x squared, which is 20x e to the x squared. Boom, it's the same. Boom, done. So that is a particular solution to that differential equation there. Right, so that's a basic introduction to differential equations. Okay, and on page 59, there's another example here, which I'm not going to write out because this video is already getting a bit long. So I'm just going to show you it, just show you another example. Only this time, we're not only finding a general solution, we're also finding a particular solution. So I'm just going to talk through this so you can see how it works. So we start off with this thing here, and again, it doesn't look like you can't instantly solve this one. You can't make it say dy dx equals a function of x, like the first example that I did. So this one must be done by separating the variables. Okay, so first job is add y squared to both sides and then divide by x squared. If you do that, you'll get to there. So they are the same. Okay, just check, pause the video if you need to, that is the equivalent. That is the equivalent of that. Then we're going to divide by y squared here and times by dx here to get to that. Stick some integral signs in front of them both and then integrate both sides. It's easy integration. It's y to the minus 2, which becomes minus y to the minus 1, or minus y over y, and similarly that becomes minus 1 over x. And then we just stick the constant on the end like that. We then want to rearrange that to make y the subject, okay, which is what they're doing on these two lines here. So with a little bit of fiddling around with that, you can get it to, I won't go through the algebra involved there, you can do that for yourself. You'll get to that, y equals x over 1 minus cx, like that. That is the general solution. Then To find the particular solution, you will need a boundary condition. You will need some extra information. And that information is here. They've written it in a bit of a funny way, so let me explain the notation here. The number in the bracket is the x value, and that's the equivalent y value for that x value. So an x is 1, y is a half. You sub those in here to discover the value of c. Okay, and if you sub that in and rearrange that, they haven't gone through the working, but you can do it for yourself, you'll see that c is equal to -1 in the case for this boundary condition here. We can then sub that into there, and we have our final solution, y equals x over 1 plus x. Now if you've got a bit of time on your hand, you could now check that that is correct by differentiating it, which you will need the quotient rule for, which I believe Miss has done with you, and then subbing it in to here. Okay, subbing the dy dx in here and the y, which you have to square in here, and checking that all that does equal 0. And it will, because that's how differential equations work. Right, I hope that my little video there has cleared that up for you a little bit, because I'm going to ask you now to do an exercise. I'm going to ask you... Oh, I'm upside down. Hang on. Here we go. I'm going to ask you to try the exercise on page... Oh, I'm all white. On page 60, which is variable separable differential equations. I will, at some point, when I get round to it, do the exercise myself and publish the results so you can check to see if you've done it correctly. Okay, I'll probably do that this week sometime, maybe not today, but I will do that for you, and you can check whether you're doing it right. Before we move on to page 61, which is where things get real, because then we're going to start to look at some first order differential equations, linear ones, for which the variable separable method doesn't work, and we need a clever technique to turn it into effectively a variable separable in order to do it. If you want to read page 61, have your minds blown, feel free, but I will be explaining that in a later lesson. Bye for now. Where's my button to turn you off? Here it is. Bye.